In Chapter 7, Section 2, we're going to talk about solving systems again, but this time we're going to do it a little differently. By the end of this lesson, you should be able to solve systems of equations by using substitution, and then analyzing the special types that we had before. So remember, there's three possibilities. These are special types. Sometimes you can get one solution. It's an ordered pair that makes both equations true. So on a graph, that was really easy to find because it was where the two lines crossed. This time what we're going to do is solve things algebraically. So you're going to get an answer for x and an answer for y. And then we're going to write it as an ordered pair. Remember, you can have infinitely many solutions, and we'll talk about what that looks like in an equation. And then you can have no solutions. So we know what this looks like when we graph it, but algebraically it's going to look a little different. So the three methods that we did that we're going to learn to solve, we've already taken care of graphing. Today we're going to talk about substitution, and tomorrow we'll talk about elimination. So the steps to solving by substitution. The very first thing that we need to do is solve one equation for x or y. The awesome thing is, sometimes this step is going to be done for us. This just means get x by itself or get y by itself. What we're going to do next is substitute. This is called substitution for a reason, so we're going to plug it in. So substitute this expression into the other equation and solve for the variable that we have. And then we are going to substitute again. Substitute your answer into the revised equation from step 1, so this thing up here, and solve for the other variable. So substitute and solve, substitute and solve. So let's do a problem. So this very first one, the first step is already done for me. Y is already found. I know that y equals 2x. So what I'm going to do is in this second equation, wherever I see y, I'm going to substitute that in. So this equation stays exactly the same. The 7x, the minus y, the equals 15. But instead of writing y, I'm going to write what y equals, and y equals 2x. And then we can see that what we did is we got rid of one of our variables. Now, if we distribute this negative, we have something with just an x in it. And this is something really easy that we can solve. If we divide both sides by 5, we get that x equals 3. So we found one of our answers. Remember, we need to get an answer for x and an answer for y. So because we know what x equals, this is where step 3 comes in. I'm going to take this and plug it back in up here. I know that y equals 2 times whatever x is. X equals 3. So that tells me that y equals 6. And instead of writing it as two separate answers, we like to combine it into one answer and write it as an ordered pair. So if I was to graph these two things, the place where they would cross is at 3, 6. And then we can check this answer by plugging it back in. Remember, this is our answer for y and this is our answer for x. Now it should work in both equations. If we plug it in the first one, does 6 equal 2 times 3? It definitely does. Second one's a little harder. We'll do 7 times 3 minus my y. I want to know if that equals 15. So 7 times 3 is 21. If you take away 6, you definitely get 15. So because it works in both equations, I know without a doubt that this is the correct answer. Now this next one's a little different because step 1 is kind of done twice. Both of these equations have y by itself. But remember what that means. It means I'm going to take what y equals, this negative 4x plus 8, and anywhere I see y in this other equation, I'm going to substitute it or replace it. So that means if I take this green stuff, negative 4x plus 8, has to equal this other stuff, x plus 7, because I replaced it. Instead of writing y, I'm going to write what y equals. And now this is an equation that everyone should feel confident solving. I'm going to move this x over here. And then subtract 8 from both sides. And if I divide by 5, I get that x is 1/5. So now that I know this, I can find y. And it doesn't matter what equation you plug this into. Let's plug it into the bottom one. It looks a little easier to me. So anywhere that I see x, remember all I'm going to do is substitute it. Plug it in up here. So that means y equals 1/5 plus 7. So if I want to add these, remember we need common denominators. So instead of writing 7, I want to do something over 5. So 35/5 is the same thing as 7. So we end up with y being 36/5. So instead of writing it as two separate answers, remember we write it as an ordered pair. So x is 1/5, y is 36/5. And we can plug this in and double check it and make sure that we have the correct answer. So let's do some more. These ones are a little tougher. If you notice in this system that we have right here, none of the variables are by themselves. But this is pretty darn close to being by itself. All I would have to do to get this y alone is add 6x to both sides. And now I have y equals 6x minus 7. So just like before, now that I know what y equals, I'm going to come up here and replace it. Substitute it in. So the 3 stays the same, but instead of writing y, I'm going to write what y equals. And y equals 6x minus 7. And then everything else stays the same, plus the 2x equals 4. And again, this turns into a nice, pretty algebra equation that we can solve. We're going to have to do some distributing here. So you get 18x minus 21 plus 2x equals 4. Combine our like terms. And then get x alone. So 20x equals 25. And if I divide both sides by 20, 5 goes into both of these, so we end up with x equaling 5/4. And then remember, once you know x, plug it in to find y. And this was step number 3, where we're going to take this and plug it in to this equation here. So I have y equaling 6 times the x that I just found, which is 5/4, minus 7. So when we multiply these together, remember multiply the tops, so we get 34 minus 7. And then we can turn 7 into something over 4, 28/4. So we end up with a nice pretty 2/4, which can be simplified to 1/2. So instead of writing this as two separate problems, remember write it as an ordered pair. 5/4, 1/2. And the whole reason we learn graphing first is because it's very visual. It's easy for us to see where the lines cross. But if this was our answer on a graph, I wouldn't be too sure if it was 1/2 or maybe if it was 1/4, depending on how small the graph was. So that's why these algebraic methods come in so handy. Alright, this next one is very similar. It doesn't have any x's and y's, but we can still solve for two variables. Before we do this, change this number to a 70. It's going to make our life a lot easier. So, step 1 is done for us. One of the variables is by itself. So since c is by itself, what I'm going to do is take what c equals and replace it with c in the other equation. So remember, the rest of the equation stays the same. You still have the 4d plus the 10, but instead of being multiplied by c, I'm going to multiply by what c equals, which is 3d minus 27. And then everything else stays the same. So now we're going to have to solve this. Do some distribution, so we get 30d minus 270 equals 70. Combine our like terms, so we get 34d. And then get x by itself, or d by itself. So if I add 270 to both sides, I end up with 34d equals 340. And if we divide by 34, we get a nice pretty number, D equals 10. So then once we know that, we're going to go and we're going to replace this again, or substitute it again up here for D and find C. So C equals 3 times the D we just found, minus 27. So is 30 minus 27, or 3. And then remember, instead of writing these as two separate answers, we want to put them in an ordered pair. So usually it's X and then Y, but because these are C and D, we just put them in alphabetical order. So C comes first, and then D. So your answer for this is 3, 10. So now all of these that we've done so far have had one solution. We've gotten an actual point for each one of these. These next two that we're going to do are our special cases. One is going to have infinitely many solutions, and one is going to have no solutions. And we're going to see what that looks like algebraically. So this first one of these is solved already. We know what y equals. So just like we've been doing, we're going to come up and plug that in. So the 4x stays the same, the minus 2 stays the same, but instead of y, I'm going to put what y equals, 2x plus 3. And everything else is the same. So then we're going to distribute 4x minus 4x, and then we'll do minus 6 equals 8. And something happens here. These cross off. 4x minus 4x goes away. We get negative 6 equals 8. And then you have to stop and ask yourself, can that happen? Can negative 6 ever equal 8? The answer is obviously no. This is not possible. So when you get a statement that is not true, that means that this has no solutions. This means that negative 6 can never equal 8. And if we were to graph these would be parallel lines. There's absolutely nothing that works. So if you're solving things algebraically and you get a statement that is not true, that means you have no solutions. So let's try the next one. Again, this is solved for us, so I'm going to take this and replace it with y here. So everything stays the same except the y part. Negative 1/2 x plus 5, and then it still equals 10. So just like before, simplify this. If we distribute here, 2 times negative 1/2 gives us negative 1x. 2 times 5 gives me 10, and it equals 10. Now again, something special happens here. I have 1x minus 1x. So again, those cross off. They go away. But this time, I get a statement that's true. 10 always equals 10. And because you get a true statement, this means that there are infinite solutions out there. That it doesn't matter what you plug in for x, doesn't matter what you plug in for y, this is always going to work. So if we were to graph this, remember this would mean that these are the same lines. So algebraically, no solutions means you get something that can never happen. Infinitely many solutions means that you get something that is always true. So you should be able to solve systems of equations by substitution. This is exactly the same problem that I gave you the night before when you had to solve it by graphing. So you can check your solution by plugging it in or by breaking out your 7.1 notes and making sure you got the same answer. Make sure you write down any questions you have, and we can go over them in class tomorrow. Have a good night.